Hello, and welcome to a supplementary lecture for the Principle of Relativity unit in Phys 1104. This video is just a place where I've dumped some Icky derivations. So in particular, there's one that's relevant to Lecture 3 of the unit, one to Lecture 4, and one to Lecture 5, and I've moved them out into this supplementary video and just summarized the derivations in the main videos themselves. So we've got our transformation equations for positions, displacements, and velocities. The logical next thing to do is get our transformation equation for accelerations. And so we're going to need to do delta v's, right? So here's your change in velocity of object O relative to u. And again, I'm going to rewrite it in terms of velocities relative to Trogdor. So I'm going to do exactly the same thing. I'm just going to replace this, and I'm going to use the velocity transformation equation. And then I'm going to do the same thing with this part. And we see something fairly familiar happen from the last lecture. Note that there is VABF and VABI, except Trogdor is moving relative to u at a constant velocity. And so I don't need the F and the I. That's just VAB. And so because of this minus, those are just going to cancel each other out. And all we're going to wind up with is, and that is just delta V relative to Trogdor. Oh. Delta V relative to Trogdor is just the same as delta V relative to u. That's nice and simple. So if we now want the accelerations, we'll do the same trick we just did. We will just divide both sides by delta t. And then again, just take the limit as delta t goes to 0, both sides. And I'll remind you that what that means is the derivative, and this is, you can think of as slopes of tangent lines, or rather that the components of each of these vectors is the slope of a tangent line. And that is by definition the acceleration. And so the acceleration in one frame is the same as the acceleration in the other. Now that we have our momentum transform, let's use it to transform the momentum of a system and see how we get to the zero momentum frame. So our momentum of a system is just a sum of the momentums of the individual objects, 1, 2, 3, and so on. And so each of those will be of this form. And so again, we can use the momentum transform equation to transform each one of those into the zero momentum frame. Now if I just collect terms, so I'm going to collect all the VAZ terms, and then collect all the other terms. And this sum of inertias here is just the total inertia of the system. And these remaining terms are just the individual momenta of the objects in our zero momentum frame. But notice that is just the sum of those momentums, and so all of this is just the momentum of the system in the zero momentum frame. So what we've got is this. But look, by definition, the momentum in the z frame is 0, and so we've just found our velocity of the zero momentum frame, just solving it out of here. And it is just the momentum of the system in our original frame A divided by the total inertia of the system. So just like last lecture, we spent a lot of our time transforming momentums from one frame into the zero momentum frame. What we need to do now is transform the kinetic energy into the zero momentum frame so we can get an idea of how we more easily calculate it to get insight into how much energy is convertible into internal energy. So here is the kinetic energy for a system of objects all moving along the x-axis, right? And we have an object 1 and an object 2 and so on. And we know how to convert this because the inertias don't change, and so now we just have to transform each of the x components of velocity into the z frame. Now notice that we have a bunch of nearly identical terms, so let's just see how one of them expands out. So that's how one will expand out, and all the rest will expand out the same way. So if we collect all the VAZX terms, we're going to have one term that looks like this. Then we can collect all of the terms of this form. The common factor in them is VAZX. And so I'm going to stick that common factor at the end of the term. And finally, these terms are all different, except they're all of the same form. So notice a few things. This is just the total inertia of the system. This is just the sum of the kinetic energies of all the objects in the system in the zero momentum frame. But the thing that's the biggest simplification is here. This piece is the sum of the momentums, but it's the sum of the momentums in the zero momentum frame. And so we know by definition that this term is 0. So that's gone. So all of a sudden things radically simplify. And we have one term like this. And then we have a term like this, which is the sum of the kinetic energies in the zero momentum frame. So I'm just going to call that the kinetic energy in the zero momentum frame of the whole system. Now let's look at the meaning of what we've got. This first part is a kinetic energy that is just like an object of inertia equal to the whole system moving along at the velocity of the center of mass frame. And so you can think of this as the kinetic energy of the center of mass of the system. And so that's what we're going to call it. We're going to call it the kinetic energy of the center of mass. And then we have this piece, which I've called K, the kinetic energy in the Z frame of the system. Relative speeds between the objects in the system, whereas this piece is really to do with the motion of the observer. relative to the system. So in other words, this piece here is the only part that is available to be converted into internal energy. And so from the point of view of what the system is able to do within itself, this is the important part. And so we will call it also, we can call it the Z-frame kinetic energy of the system, but it is also the convertible kinetic energy. Okay, we've essentially got what we wanted. We wanted a transformation that would give us the kinetic energy as measured in the zero momentum frame, or if you prefer, the center of mass frame, and that is what this is. But there's an easier way to calculate it, and it'll take just a little bit more work. So first of all, I'm going to just flip the equation around to solve for that convertible kinetic energy. Now, to simplify things, I'm going to specialize to the situation of just two objects in the system. We can do this for more, but the algebra gets much nastier. So I can now write this out in full fairly easily, because that kinetic energy in our original frame of the system is going to be like this. And I'm going to omit the A subscripts. And also I'm going to note that everything here I have velocities squared, which just gives the same as a speed squared. And so I don't need to worry about components anymore. There is the kinetic energy of the system in the original frame. And now the kinetic energy of the center of mass. And I will just write this as the center of mass speed squared, which is the same as the center of mass velocity squared. Now there is a whole lot of algebra that we could do, and which I'm not going to, for several reasons. First of all, the algebra is just a little yucky, and second of all, it actually involves a vector manipulation that we haven't seen yet called a dot product. So I'm going to leave it for later in the course. But I'll just say, if you replace this with what we know it must be, and then do a lot of rearrangement and a little bit of vector manipulation magic, you end up coming up with this remarkably simple expression for our convertible kinetic energy, where I will note that this is the relative speed, which is what we figured should be the important thing in collisions. And this quantity here we call the reduced mass, which we represent with the Greek letter mu. And the thing to note about this expression is that we can calculate it entirely using things that we knew without transforming into the center of mass frame. And so it's very easy to calculate this. And I'll just say that this thing here, the reduced mass, is going to be very important for some of you, the chemistry students. This is going to be very important in spectroscopy. It will show up all over the place in the quantum mechanics that you do to look at vibrational and rotational spectra of molecules.